diffraction means nonlinear discrete Schrodinger equations, which is a joint work with Dirk Kundermerk in University of Illinois at Urbana-Champaign. So let's see the equation we are interested in today here. So here we have a certain type of nonlinear discrete Schrodinger equation. So let me explain what this is. So here we have the complex unit I here, and derivative of u with this psi, plus some function of psi multiplied to discrete Laplacian of u here, and then we have this nonlinearity. So here u is a function of psi, where psi is in R. So, and this is the distance along the waveguide. In fact, this problem comes from some optical waveguide arrays. So here we have a certain arrays well separated. So you can think of, we have just a distance among these all arrays. So this x, which is integers here. So x is in Z, which represents the location of the array element. And psi is the distance. In each array, we have this length, right? So that variable is psi, and that location of array element are x here. And the solution of this represents the electric field propagation in optical waveguide arrays. And here is discrete Laplacian. So we have the same form for usual Laplacian you have seen so far, but this is discrete Laplacian. So this is just difference of differences in 1D. So we have some integers, okay? So when you consider any integer point x, Laplacian of u of x is difference of differences. So we have only two nearest neighbors, which is x plus 1 and x minus 1 in one dimension, right? So this is difference of u of x plus 1 minus u of x minus u of x minus u of x minus 1. And if we collect these two first, we have sum of two nearest neighbors minus 2 times function value at x. And if you consider 2D case, of course we are going to have two more closest neighbors. So just add all of values to add these closest neighbors and subtract 4 at x, etc. So such a thing is called discrete Schrodinger operator. So we have this discrete Laplacian in this form, and sometimes if you look at some paper about discrete Laplacian, sometimes they drop this constant strict. If you look at this as an operator, you can see that this thing is sum of these 2 minus 2 times function value at x is null, which gives just a shift. So if you consider a spectrum like that, then you can ignore that constant shift and then just consider sum of only closest neighbors, like that. Okay, and unusually we have some function of psi, not constant sitting there. So we have some function of psi multiplied to this discrete Laplacian, and here this d of psi is for the total diffraction along the waveguide. And let me show some picture on physical setting. So I just got these pictures from some optics papers, non-math papers. So can you see these arrays? So we have certain arrays and just emit some laser beam on the arrays and then see how this goes as psi increases. So you can think psi as like time variable to understand better. And in fact, here, because of some diffraction of the beam and self-focusing, coming from some nonlinearity, when we have very good balance between nonlinear effect and diffraction, we can have a very good self-trapped soliton, which is called spatial soliton in this setting. So there is another kind of soliton which is called time soliton, which is used on some optical fiber communication. So, you know, when we use internet, they use some glass fiber to send signal. And they use some soliton shape of signal to give fast and safe signal through this long glass fiber. And this is some different setting, and mathematically we have discrete Laplacian instead of Laplacian. So in 1D this is the second derivative, right? So second derivative. And this is picture comparing diffracting beam and soliton. And as you see, yeah, many people like to have a soliton, that diffracting beam. So how can we have such a soliton? So those how can I say, some people in optics, they use zigzagging structure to make soliton. In fact, in time soliton, in fiber optics cable, if they change the material which they use, then they can have positive dispersion, negative dispersion, positive dispersion, negative dispersion, like that. So using certain material, they can control dispersion. But in diffraction, they cannot do that. Even they change the material, it doesn't give different type of diffraction. So how they could get different diffraction is use geometry. So can you see we have some periodic structure like that, zigzagging style. So instead of using straightforward arrays, they use periodic zigzagging arrays to control diffraction. So they want to have some positive diffraction and then negative diffraction, positive, negative. So finally they could have almost zero average diffraction. And such a thing is called diffraction management. So let's go back to the math. So how can we have such a structure in math? So basically here we have that T, which was multiplied in front of discrete Laplacian. We have function of psi, which is 1 over epsilon multiplied by d sub 0 over psi over epsilon plus some constant d sub ab. Let me explain what these are. Here, this d sub 0 is a periodic function with the mean 0, so average is 0. The periodic function with average 0 over one period. And in fact, we want to have almost 0, but just unfortunately, we can have some leftover. And that is collected in this constant, which is denoted by d sub ab, average diffraction. And here we have used this epsilon, some parameter, very small parameter, positive parameter epsilon here. And as you see, here we have 1 over epsilon multiplied in front of it. That means we have very big diffraction in front. And in fact, d sub 0 is a periodic function. So when we divide psi by epsilon, of course, period gets smaller, right, by epsilon. So we have a very fast change of diffraction with a very strong power. And this kind of thing is called strong diffraction management. And plug that d of psi in the original equation, then of course and then just change the variable t, which is psi over epsilon. Easily you can calculate this one. So we have I du dt plus d sub 0 over t Laplacian over u plus epsilon multiplied by this average diffraction Laplacian over u plus u squared u equals 0. And then look at this part and then take answers, which is u equals t sub tv. So we want to consider solution of this equation. Just free operator, free equation here. So here t sub t is e to the I d over t Laplacian, where this d over t is antiderivative of this small d over 0, t sub 0. So that when we plug in this t sub tv in the place of u, just basically we need to calculate this time derivative, t derivative of u, and because u is in this form, we have something like product rule. And if u differentiate in t, then we get differentiate that we have I small d sub 0 over t Laplacian in front, and this itself with v, which is u itself. So we have this term, and here we have this t sub t of derivative of v. So rigorously, you can really use Fourier transform and then just take, find the solution and then come back. Then you can get same situation and just plug this one right there. Then what we get here is, since this is I times this one, we have negative d sub 0 over t Laplacian of u, which cancels this one. So this term will cancel that, and we get I times this, t sub t, t derivative of v, plus epsilon multiplied by average diffraction Laplacian of t sub tv, right? And plus t sub tv squared t sub tv equals 0. And then use its inverse, t sub t inverse in both sides, then we get just this itself plus this one. In fact, we can switch t sub t inverse and Laplacian, which cancels them. So we have just Laplacian of v there, and then epsilon multiplied by t sub t inverse of this t sub t v squared t sub t v equals 0. So in fact, we paid some price making this very words. So we have very nice structure right there. So, and let's see, this is a good price to pay off. Okay. And then, in fact, this is the equation we really want to learn. But this is very hard to study. So what people does is just employ some averaging process right there. So instead of using this itself, integrate this one over one period in t. And let's say the period is 1. Then instead of this, we calculate integral of 0, 1 over this in S. So I just change that dummy, just t to dummy variable S. So we have some nonlinear discrete Schrödinger equation before averaging and after averaging. And there are a lot of results about this after averaging. And there is some result to compare solutions of this and that, so that this averaging is not bad, it's good. So we didn't do something very bad. And that is by Moser in 2005. He could show that with the same initial data, the solutions of equations before and after averaging are epsilon close in this space for t or large enough. So, yeah. Yeah.
I don't quite understand the W yet. The slope part of V. What is that? The previous page. Yes.
Yeah, so they call the solution of this one, which is the slope part of W of V. So when they average it,
So what's the relation? How do you express W in terms of V, or how do you express V in terms of W?
So I don't think really we can express WL in terms of V, something like that. So somehow we have some separate equations, just before averaging and after averaging, and just to see this averaging is not so bad. So in fact, so here, how can I say? Here this small piece of 0 over S is a periodic function, right? So
you obtain the equation for W by integrating the equation for V from 0 to 1 in T.
yeah, right.
Is that right? So W,
So,
from
so basically here we have a very fast oscillation also.
Yes.
You know, this is also a periodic function, that entire derivative, because this derivative, this of 0 is periodic with the average 0. So when we integrate it, we get again periodic function, and t is like psi over epsilon. So it changes very fast. So
just naively,
yeah.
I'm always naive. Naively, if I integrate the equation for V from 0 to 1 in T, I get the equation for W, except the first term. Looks that way. I'm not sure how one gets the first term.
So it doesn't say we really integrate this one with full equation over 0, 1. Yeah. So here we have very just a fast, something like oscillation. So we just replace this by its average. So you can think of this as something like some approximation, like that.
So maybe can you explain the difference between V and take a minus V minus W, and it has some satisfying some equation? No.
I didn't really write it down, but I don't know. So just subtract these two, then. So in fact, just this can give some idea how they connect. Just not just represent one in terms of the other. Just when we have the same initial data, and then just solve the equation and then see how they look like. So for yeah, so their difference is in that space is epsilon close for large enough t. So and t here is that distance along that cable, not time, but just for large enough distance, the solutions are quite similar if we start with the same data. You see, in t we at infinity, and in x we have a small L2. Yeah, small L2. X is the integers, right? Okay. Anything else? Okay.
Yeah, well, usually in homogenization, so as we discussed, the difference is kind of considered as a correction.
Correct.
Yeah,
Okay.
then we find the equation for the correction.
And then just see the rest. So, yeah. Can I move on? Thank you. And in fact, here we have another answer. It's like some standing wave. You know, in t is the distance along that array, and just we want to have the shape not changing. So in any place we want to have the same shape. This is something like standing wave, and just using such an ansatz, the function of x multiplied by this, which is I epsilon omega t in front, and then plug this one in the equation, that average the equation, then what we are getting is this equation. So we get negative omega f equals that diffraction average constant multiplied by this discrete Laplacian of f minus q of f, where q is given just like before. Just substitute this one, and then you will get that. Okay, and then this question is related to some variational problem about this. So here we can, for existence of this stationary nonlinear discrete Schrödinger equation, we can consider constrained variational problem in this type. So we consider in theorem of some Hamiltonian where f is small L2 in Z with norm fixed as lambda here. And here this Hamiltonian comes from the equation before we had. So this average diffraction over 2 inner product in small L2 with Fn negative Laplacian f and minus part of this functional. And here this script q is just this one. So here when we have f1, 2, 3, 4, we have integral from 0 to 1 ds just like before, but here we have summation over x in z, t sub x, f1 of x, and t sub s, f2 of x with a complex conjugate, and 3 and 4. So when we plug f here, we'll get the t sub s f of x to the 4th. And here let's look at how this functional q is. So this q is on this space. Yeah. And of course this is multilinear function. Can you see? So just keep 3 of them fixed and then put some linear combination in one argument. Then easily we can see that since this t sub s is unitary operator, which is one of our linear operators, so we can just separate them easily, and summation and integral, sure. So this is multilinear functional. It's easy to see. And is it bounded? It's not that hard, but you are going to see it in a minute. And also, there is a connection between this q and script q. If you take inner product of this q with the f4, then we get exactly this multilinear functional script q. And we are going to use that. And there are some known rigorously proven results. And Moser and Panayiotis independently showed that there is a solution for positive diffraction. And since Lavoberg could show there is a solution for zero average diffraction, so we don't have that Laplacian anymore. And she could show even more that solution decays faster than any polynomial. So she had some result about decay. And then we could show this solution for average diffraction is 0. Indeed, that decays like that. So if you look at this part, if you ignore some of this, you can see this is like x to the negative x power, like a super exponential. So we could have some super exponential decay. And here we have some condition on tau, which is supremum of this antiderivative of diffraction d0t. So this one is finite. Okay. So now what I want to do is, I want to just give some idea how we could show that super exponential decay for this solution for vanishing diffraction average diffraction. Okay, so what we can do is first just let F be a solution of this stationary equation here. So omega F, so we don't have Laplacian anymore. So omega F equals Q of FFF. And we just concentrate the tail. So look at this function. For any n, which is whole number, 0 or natural numbers, and define alpha of n, which is L2 norm over f on the tail. So of course, alpha of 0 is norm over f itself, right? And easily we can see that this alpha is decreasing in n, sure, right? And this alpha decays to 0 as n goes to infinity, since this f is in L2. Yeah. And then we have two very important theorems. First, we could construct self-consistence bound, which is the following. So when we concentrate on tail, even farther down, so alpha over 2n, so from negative 2n to negative infinity, 2n to infinity, then that is bounded by, and this sim means some constant multiplied to this one, and this implicit constant is related on tau itself. And here we have that is bounded by alpha of n to the third plus such a nice super exponential term sitting there. And using this self-consistency bound, we could get super exponential decay in this form. So we had alpha of n, the tail part, L2 norm over tail, is bounded by n plus 1 to the negative mu sub 0 and plus 1 for some mu sub 0. And in fact, we could show this one for mu sub 0 less than a quarter. Okay, so from now on, what I want to do is explain how we could get this self-consistence bound, and then from self-consistence bound, how we could get this super exponential decay, if time permits. So I have 30 minutes, so let's see how much I can do. So do I go too slow or go faster? Or I'm fine? Okay. So here, so this first part is about how to show self-consistence bound. So to show that, since we know this f is solution of omega f equals q of FFF, what we do is just take inner product with any g in L2. So of course we have omega multiplied by this inner product of FGE, which is inner product of q over FFF with g, which is q over FFFG. And what we want to do is we want to get an estimate of alpha over 2n, right? So how can we get alpha over 2n? So just note that this alpha over 2n can be written in this form. Can you follow it here? So alpha over 2n is supremum of this absolute value of inner product of f with g over g whose norm, L2 norm, small L2 norm is 1, and its support is in here, from negative infinity to negative 2n, and 2n to infinity. So to get a bound of alpha over 2n, what we are going to do is just get an upper bound of this part, inner product of f with g. And what is inner product of f with g? That is just this one. 1 over omega square q of FFFG. So get a upper bound, get a bound of this square q uniform in G. Then we can get alpha over 2n is bounded by whatever we have for this uniform bound. And for simplicity, let's assume omega is 1. Okay, so now we are going to concentrate how we can get a bound for Q of FFFG, where G has supported right there with norm 1. That's what we want to do. Okay, so just let G in L2 with norm 1 and support is right there. And then what we are going to do is split this F into two parts, F small and F big. And here F small is, we just consider F itself only negative n plus 1 to n minus 1. So here we multiply just characteristic function, not smooth cutoff, just characteristic function itself, okay, on this interval minus n plus 1 to n minus 1. And from the picture, we know that support of G and support of F small are well separated. They have distance at least n plus 1, right? So what we are going to do is, using multilinearity of this script Q, just split just this functional in this form. How? Just keep these 3 and then write down F small and F big. And then F big, FFG, just separate that. So now F big, FG, fix that, and then just split the second into F small with F big. And the thing we have, which would be F big, F big, FG, we split the third one again as F small plus F big. So we get just a sum of these 4. Can you follow me? So just use multilinearity, and it's not just take one step and then second and third. So by 3 steps, you can get this 4 times. And then just we get 2 estimates. First one is about Q of F1, 2, 3, 4 is bounded by small L2, product over small L2 norm of these 4. So we are going to use this one to estimate Q of FFFG, and also it gives boundedness of this multilinear function, Q, right? And when we get that, we can see this square Q of F big, F big, F big G is bounded by norm of F big to the third multiplied by norm of G. And of course, norm of G is 1 by the setting. And what is this? This is the exact norm of F big is exactly alpha of n. Because, do you remember the picture? So this F big has support from negative infinity to negative n, and n to infinity, right? So exactly L2 normal F big is alpha of n. So we can get this part is less than or equal to alpha of n to the third. So we have that term in the self-consistence bound. And how can we get the other term in the self-consistence bound is from that. So here, if we have a distance of 2 supports, support over Fk and support over Fl has distance d which is greater than or equal to 1, if they don't overlap, we have at least 1, because we are in discrete setting here, right? So when we have a distance, then what we have is this estimate. This Q of F1, 2, 3, 4 is bounded by this very nice super exponential term, a factor there, multiplied by L2 norm of each of them. So once we get the second estimate, using the distance between support of G and support of F small is at least n plus 1, we can just plug in these 4 terms. Then we can see that this comes from this one by estimate 1. And this comes from these three. Since every term in the first three has f small and g, right? F small g here and f small g here, f small g there. So we have two functions, in fact two sequences, whose support have at least distance n plus 1. So we could get, just by plugging n plus 1 for these, we could get just this system. So once we get these two estimates, we can get self-constance bound.
So what is the exact statement of the estimate 2? Is it for some KI or for all KI?
So this is if if we have any just couple K and L, yeah, if two sequences have separate supports, it doesn't matter which one. So if two of them have separate supports, then we have this nice bound. That's the meaning. So here we are going to use f small and g for that in three of them. Okay. So can you see? Once we have these two estimates, we can get the self-constance bound. Okay. So how can you get this first estimate? Just getting first estimate is very simple. Just use small LP norm. We know small LP norm decreases as P increases, right? Since we are in small LP, we know L4 norm of F is less than or equal to L2 norm. And this T sub S is unitary, that is isometric. And just by definition and use triangle inequality, easily we can see that is bounded by that. Just can you remember the definition? Okay, and then just use the Cauchy-Schwarz twice, or just generalize Heldar also. Then easily we can see that this integrand is bounded by product of L4 norm over T sub S Fj. And then use this one to get this bound. And this T sub S is unitary, L2 norm preserves. So we have that. And then just take integral on both sides. Then we get just this one. So this gives the first estimate, and also this gives the boundedness of Schr cube. Okay? So that was a simple one. Second estimate is much more complicated than that. So here, just for without loss of generality, let's assume the first and second one, there is one missing parenthesis. Okay, so just the first and second one have well separated supports, which is greater than or equal to 1. And let's see, we can get this second estimate. So how can we get that? In fact, here, by the definition, we can easily write this one. So we have two groups here. Okay, L2 norm of product over these two, and L2 norm product of these two. And then just here, using this Freeman, take this out of the integral. And then just for this one, just like before, we can easily show that is bounded by product over these two norms, F3 and F4. And then if we can get this is bounded by that, then yeah, we can get this. And then from third to fourth here, from here to there, we can use this simple argument. So basically, if we can show this part, then we can get this estimate. And here, this function is the ceiling function. Do you know ceiling function? So ceiling function means, just the smallest integer greater than or equal to that value. Okay? So using this one, it's not hard to see why this is bounded by that. So basically, this is important thing we need to consider when we have well-separated support over F1 and F2. Why this L2 norm of this time evolution e to the IT Laplacian F1, e to the IT Laplacian F2, that is bounded by this one. That is what we now have. once we have this inequality true, then we can get that self-consistent bound. Okay? Then we can have the half of the proof. So here, to get that, we need some more. So we need lemma and corollary 1, and then we can get this second corollary, which is that inequality we want you to have. So how can we get this lemma first? So here we have this lemma. So consider supremum of this one, e to the it Laplacian, delta sub y, and delta sub x. This is just canonical delta function, not direct delta function even. So here, delta sub y of z is 1 if y and z are the same, if not 0. Yeah. Okay, so when we consider, why do we consider that? Because this e to the it Laplacian f at x can be written in this form. So to get estimate over this with f1 multiplied by f2, we want to get a bound over this one first. So how can you represent that? In fact, here we have discrete Laplacian, not continuous Laplacian. What we know is that continuous Laplacian in continuous setting, that is unbounded operator. So we cannot have such a notation, right? So when we have bounded operator, we can represent that as a sum series like that, right? And we know this one-dimensional discrete Laplacian has norm 4. Yeah. So using this, we can get this bound. It's not that bad. So just plug in. So using this one and just plug in here. No problem. And then see. Here we have nth power of Laplacian. And do you remember how this discrete Laplacian connects the values of functions? Here we have delta function. Just only at y we have 1. And only at x we have 1, right? And here is delta sub n. If this distance between x and y is less than n, which how many times we apply this discrete Laplacian, we get 0. We cannot connect anything if they are too far. Do you see? Because this discrete Laplacian connects the value to only the nearest neighbors. So when you take twice, you can get some connection with just one more nearest neighbors, right? Can you see? So exactly this sum is the same as n starts from distance of x minus y to infinity. Yeah, and then just put this absolute value inside, and here this Laplacian is bounded operator with norm 4. So this 4 to the n comes from this Laplacian to the n. And norm of delta sub y is of course 1, and delta sub x is of course 1. So we get 4t to the n divided by n factorial. This one. Yeah. And then just change the value, not variable, index here. So change the index, which is L equals n minus absolute value of x minus y. Then we can rewrite in this form. And then we separate this top part in this product of these two, and bottom part, which is, this one, n plus n factorial is of course much bigger than n factorial multiplied by n factorial, right? So we can just see that this is greater than or equal to product of this and that. So together we can get this bound, right? And look at this. Isn't it very familiar to you? That is just e to the 40, right? So we have this one when we take supremum over that interval. So it's not that at all. So since we have a bounded operator, such a calculation is diffraction is possible and just very simple. Okay? Okay. And how can you get this first corollary? Just using the one, that lemma we had, and then just plug in here. So just instead of just what? This is that we have a square here, and we have a summation over y, such that y has distance from any fixed x, at least d. So this is some uniform bound in x also. So we can show that it is bounded by this vector here. So just use the lemma itself, we just square it, then we can get actually 8 tau, and in fact we are going to start with 4 tau to 2 times x minus y. And here also x minus y factorial squared, and x minus y is greater than d. And then just change that index, x minus y by y, then we get just this form. And then just change the index here again as L equal n here. So n equals y minus t or so. But here in that integer, we have 2 points with the same length, right? From positive 1 and negative 1. So we have these two out of there, and then just change that index, we can get that, and just similarly we can get such a good bound. So this is just using the lemma itself. Then we can get this that inequality which finishes that self-consistence bound. So somehow I feel sorry about this I and L. So capital I and is uppercase I and lowercase L look the same. So this is I sub 1. So I sub 1 for supporter wave sub 1 and I sub 2 for supporter wave sub 2. Okay, so let's just call I sub 1 and I sub 2 for supporter wave 1 and F2. And what we are going to do is we are going to just classify points on that integer, which just in every point, let's see that point is closer to I1 or close to I2, like that. So here this I1 prime means so distance from I1 is smaller than distance from I2. And I2 prime is for the other, so greater than or equal to. So collect or just separate all integer points in this I1 prime and I2 prime. And then what we can see here is if we consider distance of I sub 1 prime and I sub 2, or distance between I sub 2 prime and I sub 1, we have at least this distance. So just simple, yeah. And then what we are going to do is to get this estimate, consider this one in these two sums when x is in I1 prime and when x is in I2 prime. And just get an upper bound for each of them. In fact, I'm going to show one for this, and you can get the other one for that, similarly. So how can we get such a bound? In fact, we are going to use this one. So here we know this it Laplacian f2 of x can be written in this form using the kernel, and then just use Cauchy-Schwarz, and then we can get that. Then that is the sum, first sum we want to estimate. So look at this one. So here we summarize over x in only I1 prime here, right? And then just use this one in the place of that. So plug in right there, okay? And then what we can do is just this comes from that, you see? And here we have a summation over x in I1 prime and summation over y over I2. X is in I1 prime, y is in I2, so we have at least certain function of d over 2 distance, right there. And then just take this supremum over x, then we can get out of this one from that summation, so we have a certain quantity right there. And then just consider that. So here x is I1 prime, y is I2, so basically what we need to do is just make summation over only these y's. Because x and y have at least distance, certain function of d over 2. And just consider that. And in fact, we have considered how this is, right, in that corollary 1, right? So use that corollary 1 to get this one out of this. And how can you get that from this? Yeah, that is easy. This is just this one. And we know that this, it is it Laplace F1 over x squared over only x in I1 prime. Because that is less than or equal to this one, full length. And this is unitary, isometry, so we get just F4. F2 norm over F1. So it finishes that self-consistence bound. And now time for super exponential decay. And I have 6 minutes. So what can I do? So basically, to prove this theorem, we need to use alpha is non-negative and decreasing and equals to 0 at infinity, and just use this self-consistence bound. And then we could get this super exponential decay. And yeah. And maybe you can guess how we can get that from, well, this from this. This is already in some super exponential term sitting there. And in fact, here we have alpha over 2n. In fact, if I remember correctly, so we have used alpha over 3n, something like that, for continuous setting. So here we could have some bare estimate giving alpha over 2, comparing alpha over 2n and alpha over n. And also we have very nice, this super exponential term added to it. So that this gives very nice decay of alpha over n, which gives super exponential decay. And I think if I start the proof, then I'm going to take more than 20 minutes or so. So maybe it's better me to start here. And if some of you are interested in how we can get this this super exponential decay from self-consistence bound, then I can give this PowerPoint to you, or I can explain how we could calculate it. So thank you.